Hi everyone, welcome back. This is the 12th lecture of EE635 Applied Linear Algebra. My name is Debisattam and you're watching the second module of the 12th lecture. So we are trying to figure out what to do when a matrix or a linear operator is not diagonalizable. We've seen that the next best thing is to make it block diagonal. And the key to do a block diagonalization is to decompose the entire finite dimensional vector space into a direct sum of smaller subspaces, each of them being A invariant, where A is the linear operator, right? Then it breaks up the whole, so if you take, say V is equal to W1, direct sum W2, direct sum dot 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 up to WR, and then you choose basis for W1, say B1, for W2, say B2, and so on up to for WR, let's say BR. And then you combine these basis vectors together to form the basis of the entire vector space. Then under that basis, our linear operator is going to have the structure of a block diagonal matrix, where each block, so the ith block will have size equal to the equal to di by di, where di is the dimension of the subspace Wi. Right? So far so good. No issue with this analysis, but the question, the central question is that how do we get that decomposition? Yeah, so given a vector space and a linear operator, of course finite dimensional vector space, how do I decompose this vector space into smallest possible A invariant subspaces so that their direct sum is the whole space, right? The key surprisingly lies into the algebra of polynomials. Yeah, that's what we're going to explore in this module. So let me share my screen. Yeah, okay. So how do we get these? How to do the following? How to get V equal to W1 direct sum dot 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 WR. How do I do this? Right? The key, as I said, lies in the idea in the algebra of polynomials. Okay. So we have already seen some hint of polynomials, and we have seen that, okay, this is the polynomial set of all polynomials with coefficients coming from the field F, polynomials in S, the unknown variable S. Suppose F is a typical polynomial there. F would be written as Fs equals A0 plus A1 times S plus dot 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 up to A, okay, let's say AM S to the power M, right? Corresponding to this one also has this operator polynomial Fa, as we have seen before. What we need to learn now, so what we have also seen is that these subspaces kernel Fa, these are A invariant. These are A invariant. Okay, why am I writing R? I should write is. This subspace is A invariant. Yeah. But then, how to get such a polynomial for which this kernel Fa is non-trivial? Yeah. How to get Fs such that you understand, no, Fa such that no such that kernel Fa is not just the zero subspace. You understand, no? Like suppose I take lambda I minus A. Yeah, so my Fs is lambda minus S. Now, for arbitrary lambda, only if you choose very specific eigenvalues lambda, then and only then lambda I minus A's kernel will be non-trivial. Otherwise, it will be just zero subspace. No, so they're not interesting. With zero subspaces, I cannot do anything. So this wi's that I've written, v equals w1 direct sum w2 and so on, these are all non-trivial subspaces, non-trivial A invariant subspaces. Trivial subspaces don't help, so I need non-trivial A invariant subspaces. What do I do? So how to get polynomials such that kernel of f A is non-trivial? It's A invariant, all right, but how to make them non-trivial? And that is where, in order to understand how to get these polynomials so that I get non-trivial subspaces, non-trivial whose kernels are non-trivial subspaces, I need to look at the algebra of these polynomials in a little more detail. Yeah, that's the key observation, right? So what sort of detail are we talking about? The first thing is to understand, is to appreciate that this set fs, the polynomial, the set of all polynomials, this set also has a structure. It's almost like a field, not quite. What is that? Well, such a thing is called a ring, right? So that is what. So first observation is that fs is what is known as a commutative ring with 1. What does this mean? This means that fs satisfies all the properties or all the axioms of a field except for one, namely fs need not contain inverse and contain multiplicative inverse for all non-zero elements in fs. So I hope you understand what I mean by this property. It's called a commutative ring with identity or commutative ring with 1 when it has all the properties, satisfies all the axioms of a field, only but one, namely that it need not have multiplicative inverses for all. Yeah, some may have multiplicative inverse, some may not have multiplicative inverse. We don't insist on that. So remember the axioms of a field. There's two operations, addition and multiplication. Addition has additive identity, addition has additive inverse, and multiplication has multiplicative identity and multiplicative inverse. And then there are associativity, commutativity, and distributivity properties, right? Now among all these properties, just take away the property that every non-zero element has an inverse. Get rid of that one. So relax that condition. What you get is what is known as a commutative ring with identity. So of course, because I'm relaxing one condition, it means every field is by default a commutative ring, but not every commutative ring is a field. Fs, that is the set of all polynomials with coefficients coming from the field f in the unknown s, polynomials in the unknown s or variable s, is such a commutative ring with identity with 1. Indeed, you can check that fs closed under addition closed under multiplication, yeah, additive identity is there, namely 0, additive inverse is there, namely f has minus f, yeah, then addition is commutative, associative, multiplication is commutative, there is multiplicative, multiplication is also associative, there is multiplicative identity, namely 1, but there is not necessarily multiplicative inverse, because say if there is a polynomial f which is such that f is from the field, that is just a constant, and f is also not equal to 0, then f as an inverse. But if it's not a constant, then it doesn't have an inverse. Like for example, think of 1 plus s. 1 plus n inverse is not a polynomial. You may argue that no, there is a formal power series, but that's a power series, that's not a polynomial. For a polynomial, this degree is always finite. This number s to the m, this number m is always finite. Yeah, when it goes beyond anything, any bound, that's a power series, that's a formal power series, that's not a polynomial. Okay, right. So this is a polynomial ring. All right. There are other examples of rings also, like for example, the set of integers is a ring. It's a commutative ring with identity. Commutative ring with identity. There are plenty of such examples, but we'll not be interested in that. We'll be interested only in polynomial rings. Now, in polynomial rings, so you see, because it's polynomials, we can do all sorts of things, like we can, we can do long division, we can do division with remainder, all sorts of things we can do. Like if we have a polynomial gs and a polynomial fs, both of them are polynomials, then we have this identity that there exists a polynomial rs and a polynomial qs, both are polynomials, such that, yeah, such that, well, you see, f s is equal to qs into gs plus rs with degree of r strictly less than degree of g. This is dividing f by g. This is called the quotient, this is called the remainder. The property of the remainder, the defining property of the remainder is that its degree must be strictly less than the degree of the divisor. So this is the so-called long division. This is going to be crucial for us. What you need to appreciate at this point is that because these are polynomials, this is an identity. This is true for all. It doesn't matter what, if you put a value for s or you do something else, as long as s square and so on, and their linear combinations, their finite linear combinations, is something that we allow, that we so as long as we allow such things to have a meaning, right, this would be true, this identity would be true. This is not an equation, this is an identity. What I'm trying to say here is that this also means, let me write it down in red color so that you remember this. So this actually means that if I have a matrix instead, or a linear operator instead, and look at the polynomial linear operator fa, then this would also be true, this identity, with matrices and matrix products and things like that. Yeah, and many more such properties we are going to explore, which will be important for us, right? The next thing that's going to be important for us is the idea of what is known as an ideal. Right? So what is an ideal? An ideal is in fact a set, say within the polynomial ring. So it's a subset is said to be an ideal if the following are true, if the following hold. What is it? Number one, for all f comma g in A, f plus g also in A, which means it's closed under addition. And secondly, for all f in A and p in the ring itself, p times f is in the ideal A. So for everything in the polynomial ring, you multiply things. So it's not closed under multiplication. It's not just closed under multiplication uh, within A, it's also closed under multiplication from things in Fs, right? So it's almost like a vector space sort of a structure, that it's closed under addition of elements within the set A, but it's also closed under multiplication from things outside. From you take anything from the ring and multiply it to something in A, it's going to be in A. Yeah, then it's going to be called an ideal, right? So we can look at examples of ideals, like number one, say I look at all those polynomials. So all those polynomials, say f in F such that f is equal to some gs into, say, s minus 1. This is going to be an ideal. This set is going to be an ideal. You can check, like, so suppose I have f1 and f2, both are in this set. So let me call this set A, by definition. So both are in A. Then this means what? F1 must be equal to some g1 times s minus 1. Let me write it properly. I'm writing that argument and also not writing it sometimes. Let me not do that. Let me just do it properly. Yeah, and f2s must be equal to g2s into s minus 1, right? Now check, if I do f1 plus f2, what do I get? I get f1. Okay, this is g1s into s minus 1 plus g2s into s minus 1, which is equal to g1s plus g2s into s minus 1. That's it, no? So which means that this is inside the set A, so it's closed under addition. Further, suppose f is equal to gs into s minus 1, and let's say ps is any old polynomial in fs, whatever it might be, then ps times fs is going to be ps gs into s minus 1, which also has the same structure as any old polynomial in A. Look at how they are defined. Some polynomial times s minus 1. That is what it is, no? Right? So it's, then it satisfies both the properties of the ideal. So what is this set, by the way? This set, notice that this set is nothing but the collection of all multiples of this s minus 1. So not just s minus 1, you can go ahead and check that any such set which contains all the multiples of a given polynomial. So a set defined as containing all fs in fs such that fs is equal to some, what should I write, some as times gs. So given a polynomial gs in fs, define this set, define A as this collection. This is an ideal. This is an ideal. This can be called the set of all multiples of the polynomial, of the given polynomial gs. This set is denoted by ideal denoted by this and called the ideal generated by G. So once again, ideal generated by G means generated by G. This means the set of all multiples of G, all possible multiples of G. Yeah. Similarly, one can look at ideals generated by more than one element. Namely, we can have something like G1 dot 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 up to GR, which is by definition the collection of all all polynomials. I'm getting rid of the s. Yeah, it's understandable. Dot 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 up to FRGR, where F1 dot 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 up to FR are all possible polynomials in the ring. So this is ideal generated by G1 up to GR. This is also an ideal. One can go ahead and check that it satisfies both the properties of an ideal. Right? This goes to you as a homework. Check that this is an ideal. You can do some further homeworks, like for example, check whether the following sets are ideals or not. Check whether the following sets are ideals or not. Number A, all polynomials for which the constant term is equal to 0. Yeah, what is constant term? Well, look at the typical expression of a polynomial. Where is it? Where is it? Where is it? Where is it? Oops, I've moved a little. No, not yet. Yeah, this is the general polynomial. This term is called the constant term. Constant term. Yeah. So here is the set which contains all the polynomials for which the constant term is 0. Check whether it's an ideal or not. Then B is, say, collection of all polynomials that whose polynomials that contain only even degree terms. Same, repeat, all polynomials that contain only odd degree terms. Yeah, check whether these are ideals or not. All polynomials that evaluate to 0 at s equal to 1. All polynomials that evaluate to 1 at s equal to 0. Check whether these things are ideals or not. Okay, do this homework. Now, Fs is a kind of a special polynomial ring. I mean, a kind of a special ring. Why? Because it's also an integral domain. Yeah, or ID. Fs is an ID. What is meant by ID? This means that f and g, I take arbitrary f and g. Suppose f product g is equal to 0, then this implies either f is equal to 0 or g is equal to 0. I mean, two non-zero polynomials product cannot be a 0, cannot be the 0 polynomial, right? That's if a ring satisfies this property, it's called an integral domain. So Fs, of course, is such an integral domain. But that's not the most interesting thing about Fs. Fs has one more very crucial, interesting property. What is that? So ideals that are generated by single elements, ideals generated by single elements are called principal principal ideals, right? It so happens that in Fs, okay, before we come to Fs, so right, so in a commutative ring with multiplicative identity, if commutative ring, yeah, okay, let's not use commutative ring, let's use this one. In an integral domain, if every ideal turns out to be a principal ideal, then the integral domain is called a principal ideal domain, or a PID in short. I hope you are getting my point. What I'm saying here is that in an integral domain, suppose whatever the ideal may be, you will always be able to write it as generated by a single element. It's an ideal generated by a single element. You will be able to find that single element which would generate this whole ideal. If that is true for every possible ideal, then that integral domain is called a principal ideal domain, and it so happens that Fs is a PID. Fs is a principal ideal domain. So I have already seen that it's an integral domain. We just have to prove that it's a principal ideal domain. That is, every ideal is principal. How do we do this? Let's see. Okay, so suppose A is an arbitrary ideal in Fs. Yeah, arbitrary ideal. Ideal, yeah. Any arbitrary ideal, we don't care. Some ideal. Now notice it's a subset of Fs, no? And every element in Fs has a degree, namely it's the um, the degree is, so we look at all non-zero terms. Among those non-zero terms, that is, the coefficients are non-zero. Among all those terms, the non-zero terms, I look at the guy with highest power. That is called the degree. That number, that power is called the degree of the polynomial. We all understand what degree of a polynomial is. So that is the degree. So then among these polynomials in A, I can find a polynomial whose degree is the least. So suppose let G be defined as the defined as a polynomial with polynomial A, I have to write non-zero, huh? This is very important. A non-zero polynomial whose degree is the least among non-zero elements in the ideal A. What is the guarantee that such a polynomial would exist, such a G would exist? Well, it's very simple. You see, G contains non-zero polynomials. Now, otherwise, the trivial ideal. Trivial ideal means it's only zero is there, and zero is the generator, so it's principal. But we're talking about non-trivial. So because it's non-trivial, there will be non-trivial, non-zero elements in the ideal. And if there are non-zero elements in the ideal, now notice what could be the degree? Degree could be 1. Yeah. Degree could be 0 also. In that case, it's constant, and you can check that if there is one constant, then obviously if the constant polynomial, let's say 10 is there, then 10 inverse must also be there, because not 10 inverse, then 1 must be there. Why? Because 10 inverse is an element in the ring, and multiplying 10 inverse with 10 will be 1. That should be there in the ideal by the definition of ideal. So 1 is there in the ideal. So if there is one non-zero constant in the ideal, then 1 is also there in the ideal, and the moment 1 is there, the whole ring is also there, right? So here are the two things that we have to make sure, that these are two uninteresting cases: a equal to only 0 and a equal to 1, that is the whole ring. We have to exclude these two cases. These are trivial cases. So we may assume that it's not this situation. So if that is the case, then there are these non-zero, non-constant polynomials in A. So among these non-zero, non-constant polynomials, because it's non-constant, then its degree could be at least 1. Yeah, if not 1, then 2, if not 2, then 3, and so on. So there is a lower bound to these degrees. That's what I'm trying to say. Among the polynomials in A, there's a lower bound, yeah, given by 1, can be less than that. So if there is a lower bound on these numbers, so if I look at all the polynomials in A and only collect their degrees, then that's a set that is lower bounded by 1. Because it's lower bounded by 1, there must be a lower bound. So there is a least degree. Because there is a least degree, there is also a polynomial with least degree, and that is what this G is. That is the guarantee for existence of G. Okay. So existence follows from the fact that the set of degrees of non-zero polynomials in A is lower bounded by 1. So it's a subset of non-negative integers, positive integers, and lower bounded by 1. So therefore there will be a lower bound. There is a least degree, so there is also a least degree polynomial. Now we claim that A, so this is the claim. So we want to prove that A is principal, right? We claim that A in fact is generated by G. That means every element must be a multiple of G, then every element in A must be a multiple of G. Yeah, why? Proof by contradiction. Suppose not, then that means there exists F in A such that F does not belong to G. Right, we have to show that A is equal to G. Of course, G is an element of A, so this is always true. But we have to show this direction also, that everything in A must be an element of G. So therefore, I am trying to show that. So I'm picking an arbitrary element F in A, and I'm claiming, suppose I'm assuming that F is not in G, we'll get a contradiction. Because F is not in G, so F is not a multiple of G. This means if I try and divide F by G, I must get a remainder. This implies F can then be written as some Q times G plus R, such that degree of R is strictly less than degree of G. Yeah, now this is a contradiction. Why? Notice, this is the situation. This means R must be equal to F minus Q times G, which is the same as F plus minus Q into G. Now G is in the ideal by definition, F is in the ideal by assumption. Because G is in the ideal, minus Q, and minus Q is a polynomial. So by definition of an ideal, this must also be an element in the ideal. So I have one element F in the ideal, another element minus Q times G in the ideal. So their sum must also be there in the ideal. The whole thing is there in the ideal, which means R is a polynomial in the ideal. But that's a contradiction. Why? R is in the ideal and its degree is strictly less than the degree of G. G is the least degree. So this is contradictory to G having least degree. Great, no? The only option left is that what we had assumed must be wrong, that F is not divisible by G. That's wrong. So G must divide F. So this implies G must divide F, which implies F is in the ideal generated by G. That's it. Done. So it's a principal ideal. Moreover, if G is assumed to be monic, I'll tell you what this means. Assumed to be monic. What does monic mean? Monic means that the highest degree coefficient of G is 1, right? Then G becomes unique. Right, because it's kind of understandable, because if G is not unique, then suppose we have two monic polynomials which generate the ideal, say G1 and G2 both monic, generate A. In that scenario, G1 minus G2 must also be there in A, but G1 minus G2, see, degree of G1 minus G2 must be strictly less than degree of G1 is also degree of G2. Yeah, because you see, we have already figured out which polynomials generate the ideal, namely those which have the least degree, and that least number must be the same. And so if both are monic, then both have that degree coefficient equal to 1. So when I subtract one from the other, that cancels out, right? But because G1 and G2 both are there in the ideal A, their difference must also be there in the ideal. Yeah, from the property of ideals. So here is a contradiction. I have a strictly lesser degree polynomial, namely G1 minus G2, which is also there in the ideal. So this is contradictory. Once again, to the same fact that the degree is least. So therefore, what follows is that when I assume that this guy is monic, then it becomes unique, right? Now we come back to our linear operators and their the diagonalization business. So this was an aside. This was about polynomials. This will be useful for us, and some more facts also will be useful for us as we proceed. But then, for the time being, this is enough for us to know about the polynomials, and we'll see a consequence of these definitions, namely the following. So notice, listen very carefully. We define the following set. Okay. So A is a linear operator from a vector space to itself. V is a vector space over the field F, and dimension of V is finite. So it's a finite dimensional vector space. Yeah, A is an operator. Okay. Define this set of polynomials Fs in Fs such that if A, that is the polynomial operator, is the zero operator. So zero operator. So this symbol means that the space of all linear operators from V to itself, right? Well, of course, this is a subset of the polynomial ring. This is a collection of polynomials, so it's a polynomial ring. It's a non-empty set because zero polynomial is always there, right? So it's a non-empty set. What is so special about this? Well, just notice that this is an ideal. This is called the annihilating ideal of A. We call it an A. Right? This is an ideal. Why? Check. So let us check that this is an ideal. What we have to check? Sum of two polynomials in the set must be there in the set again. So suppose if one is in the annihilating, so we call that if one is an annihilator. If one is an annihilator, right? And f2 also suppose is an annihilator, then this means f1a is the zero operator, f2a is the zero operator. In terms of matrices, these are matrices, right? Zero matrices. If a is a matrix, then f, what we are saying is f1 is a zero matrix, f2 is also the zero matrix. Of course, if I take now f1a plus f2a, that also is the zero operator. This implies f1s plus f2s is also an annihilator. That's it. So it's closed under addition. Let Ps be any arbitrary polynomial, then Pa times Fa, sorry, f1a, let's say f1 f2 doesn't matter, say f1 is an arbitrary polynomial. So if f1 is an annihilator, then f1a is 0, so this is 0, so this whole thing must be 0, which means pretty trivial stuff, huh? Which means if okay, sorry, which means Ps times f1s is also an annihilator. So the set annihilator is closed under addition from closed under addition of elements from the set and closed under multiplication of elements from the set and anything from the ring. So it's an ideal. So this guy is an ideal, annihilator is an ideal, annihilating ideal. But annihilator ideal is an ideal in a PID. So that means there exists a polynomial, a monic polynomial, unique monic polynomial, a unique monic polynomial, let's say mu in Fs, such that n A is equal to the ideal generated by mu. This polynomial mu s is called the minimal polynomial of the operator A. Like we have characteristic polynomial, we have one more polynomial called minimal polynomial, right? So what is the minimal polynomial? Minimal polynomial is the unique monic generator of the annihilator ideal of the operator A. But we already know that how to get generators for ideals like this, ideals in a one variable polynomial ring. How do you get? Namely, choose the monic polynomial whose degree is the least. So from that point of view, minimal polynomial can also be defined by saying that minimal polynomial is the unique least degree polynomial that takes the operator A to 0, or the least degree monic polynomial, monic annihilator polynomial. The least degree monic annihilating polynomial of the operator A. That's the minimal polynomial, right? So let us make ourselves conversant with this idea of a minimal polynomial. So like for example, let us suppose we look at the matrix A, which is say 1, okay, let's say is lambda 1 0 0 lambda 2. So diagonal matrix like this, and suppose lambda 1 is not equal to lambda 2. What is this minimal polynomial? How do I get this? I can notice that if I look at lambda 1 identity minus A, this happens to be 0 0 0 lambda 1 minus lambda 2. And also if I look at lambda 2 identity minus A, then that must be equal to lambda 2 minus lambda 1 0 0 0. If I now look at the product of the two, lambda 1 identity minus A into lambda 2 identity minus A, if I look at the product of the two, that's 0 0 0 lambda 1 minus lambda 2 product lambda 2 minus lambda 1 0 0 0. Take the product, you get 0. So here is a polynomial which is an annihilator. This means S minus lambda 1, S minus lambda 2 belongs to annihilator, right? But if such a polynomial is there in the ideal and mu generates the ideal, then mu must divide this polynomial, right? So mu divides S minus lambda 1 and S minus lambda 2. Lambda 1 and lambda 2 are distinct. So therefore mu could either be this polynomial or this polynomial or this polynomial. So three choices for mu: either mu is exactly equal to S minus lambda 1 into S minus lambda 2, or equal to S minus lambda 1 or equal to S minus lambda 2. These are the factors. Mu has to be a factor because mu divides it, right? But you can check that this neither this operator is 0 nor this operator is 0. Yeah, indeed, lambda 1 identity minus A is not the 0 operator, neither is lambda 2 minus A. Okay, so therefore neither this can be an annihilator nor this can be an annihilator. So that must be this is the choice. So mu must be equal to, the minimal polynomial must be equal to S minus lambda 1 into S minus lambda 2. Right? Do the same thing for this situation. So this goes to you as a homework. Try and find out the minimal polynomial of MP of A equals say lambda lambda 0 0 0 0 0 lambda 1 lambda 1 lambda 2. Find out the minimal polynomial of this. Also find out the minimal polynomial of lambda 1 1 0 lambda 1 0 0 0 0 lambda 2. Of course lambda 1 is not equal to lambda 2 and lambda 1 is not equal to lambda 2. For these two situations, find out the minimal polynomials, and you will see that although they have the same characteristic polynomial, their minimal polynomials are different. You should be able to show that here the minimal polynomial is S minus lambda 1 into S minus lambda 2, whereas this one has S minus lambda 1 square S minus lambda 2. So it seems that this minimal polynomial holds the key to understanding whether the matrix can be diagonalized or not, and also if it is not diagonalizable, then what to do next. Yeah, how to get block diagonalization. We'll see that very soon. But at least I want you guys to feel comfortable with the idea of minimal polynomials. Yeah, in the book, if you look at the exercises, there will be plenty of such problems for finding out minimal polynomials. I will also supply some problems in the assignment sheets about finding out minimal polynomials. Okay. Now, but this definition of minimal polynomial, that is the least degree monic annihilator polynomial, using that definition to find out minimal polynomials for a given linear operator or a matrix is kind of difficult. So we have to devise other ways of finding out the minimal polynomial. And we'll see one of these methods in the next module, right? Yeah, so we'll see such a method in the next module. And then we'll see this amazing fact about this minimal polynomial that actually gives us the you know the sought after decomposition, direct sum decomposition of the whole space into A invariant subspaces. Okay, so you please solve this homework problem and let's meet on the other side of the break. Okay.